In this video, we are going to explore the Williamson ether synthesis as we begin to look at ways to create ether reaction products. This name may seem familiar to you because this was covered in Organic 1 as well, so this is a bit of a review reaction. In this reaction, what we are going to be doing is taking a metal alkoxide, the M here stands for metal, so it's a metal oxygen bond there, it's an ionic bond, so the oxygen here is an anion, and that oxygen anion is highly nucleophilic, and so what will happen is the nucleophilic oxygen atom, when placed into an environment with an alkyl halide, is going to come over using its lone pair of electrons to attack the carbon that is directly bonded to the leaving group halogen to form a new carbon-oxygen bond, creating the carbon-oxygen bond of this ether product and resulting in the release of this X-halogen anion in an SN2 type reaction mechanism. So let's take a closer look at this Williamson ether synthesis and what we can do to set ourselves up for success in carefully selecting the alkyl halide and the metal alkoxide reactant to design this to steer the reaction toward a high SN2 reaction yield. In designing our Williamson ether synthesis reaction, we have to keep in mind that the reaction follows an SN2 mechanism. That was the nucleophilic substitution reaction where the nucleophile came in and attacked the electrophilic carbon at the same time the leaving group left. And so the features that previously encouraged nucleophilic substitution via this SN2 mechanism will also be true here. And one of those features of an SN2 mechanism was that SN2 worked best at primary carbons that were bonded to the leaving group. And I'll call the leaving group X here because it's typically a halogen. SN2 worked in some cases at non-sterically hindered secondary carbons, and SN2 does not work at tertiary carbons because the tertiary carbon is too sterically hindered by alkyl groups that surround the carbon leaving group bond and prevent the nucleophile from attacking that carbon that's bonded to the leaving group. And so in order to set up an effective Williamson ether synthesis reaction, we have to design this so that the R group, specifically the carbon that is bonded to the halogen, must be a primary carbon. If it's a secondary or tertiary carbon, you will end up with lots and lots of elimination product because the secondary and tertiary carbons are going to be more prone to that E2 elimination mechanism where the oxygen anion acts as a base and grabs a proton, eliminating that proton and eliminating the halogen atom to create an alkene product. So if you use a secondary or tertiary carbon here, you're going to get an E2 reaction that will yield an alkene product following Zaitsev's rule. So that is some review from chapter 7 or so there. So in order for this to work, we need the CX to be a primary carbon. That is the first and foremost thing here to remember. That is the difference between make or break of this reaction, is that the carbon that's bonded to the leaving group needs to be a primary carbon with as little steric hindrance as possible for this to work well. Now, in this reaction, what's going to happen is I will draw in my bond between R and X in blue there, and then our metal alkoxide here the structure of this alkoxide group is flexible. So this alkoxide group that we use here in our metal, it's okay if that has steric hindrance. That's not going to impact dramatically whether the reaction is able to undergo SN2 or not, because the oxygen atom, no matter how much steric hindrance there is in the alkyl group, the oxygen is still going to be exposed enough that it can act as a nucleophile, come over and form a covalent bond to the carbon that's bonded to the leaving group as the leaving group leaves in this SN2 reaction. So the metal alkoxide, you can have a variety of different structures, a wide range is possible there. So the limitation of this reaction is really you have to design it so that the carbon that's bonded to the leaving group is your primary carbon. The metal that will be used here in our metal alkoxide is generally going to be sodium or potassium as our most common ones here. It's going to be those group 1 metals, the ones that are in the first column of the periodic table, because those are going to be the +1 counter ion to the oxygen, which has a -1 charge. So when we think about what is actually present here in solution, this actually exists as M+, so it'd be like sodium plus, and then OR, and that oxygen is what carries our negative formal charge. And so that negative formal charge allows that oxygen to act ideally as a nucleophile. By definition, the nucleophile comes in, attacks the carbon atom here as the leaving group leaves to give us that new carbon-oxygen bond. The new carbon-oxygen bond in our product is what I'm highlighting in green here. That's the bond that we formed by our electron pushing arrow here. The leaving group X left, and that would create what we were calling MX over here, which is actually M+, and X- if you want to write out all the full detail there of our cation and anion that have that ionic interaction going on. So now with some of those basics in place, with some R groups that are pretty generic thrown in, let's hop into applying this toward some actual reactions with real life atoms present. So we'll take a look at this example problem. If you're feeling pretty comfortable with this, you could go ahead and give this a try on your own and then hit play after you have paused to do this to check your work. So I'm going to start with our starting structures here. And you might be asked, what is the product or products of this reaction? You could also be asked about the mechanism for this reaction. So what we'll do here is we will provide the mechanism and the major organic product or product. So writing out the mechanism, that is our set of electron pushing arrows and steps that allow us to go from the starting material to the product here. For an SN2 reaction, where we are working under these anionic conditions, we can do this as a single step. So in that single step SN2 mechanism, we draw out our nucleophile structure. Our nucleophile structure is this oxygen as the business end of our molecule. I'm just going to sprinkle in the sodium here as a counter ion. That sodium is just a spectator, so it's not truly essential that you list it in there. Then I'm drawing my line angle formula for my alkyl halide, like so. Drawing in my lone pair electrons, which is a good way of bookkeeping when you are writing out reaction mechanisms. Now what we're going to do is take the lone pair electrons here that I've circled, bring those over. They are eager to react with something. What is available for them to react with that will be very appealing to them is this carbon right here that I'm circling is very electrophilic. It's electron poor because it's bonded to the very electronegative chlorine that's pulling electron density toward the chlorine away from the carbon. So that nucleophilic oxygen with its wealth of electrons comes over, forms a bond to the electrophilic carbon, like so. So the arrowhead indicates where that bond between oxygen and carbon will be formed. And then in order to not exceed the octet rule, we have to break away this chlorine atom, and that works really well because the chlorine-carbon bond is weak, and the product that results from that, that is the chloride anion, is very stabilized because chlorine is very electronegative, so it doesn't really mind having that negative formal charge on it. And two of those electrons that we see in the final chloride product, are derived from breaking that carbon-chlorine bond. Then the product that we are interested in here primarily is our organic product. So we have our aromatic ring directly bonded to oxygen. Oxygen still has two sets of lone pair electrons that I sketched in. I'm going to draw the newly formed covalent bond in red, like so. And then the rest of that group that it's now bonded to, our full alkyl group, I'm going to sketch out here as well. So our full group that it's bonded to, making sure that I have accounted for all of the carbon atoms and that they're in the right place. We have one carbon here in our alkyl halide reactant toward the middle of the screen, two, so it's two CH2s. I have that here and here in the product. That's here, and then followed by this isopropyl terminal, which is out here. So we've accounted for all of the atoms in our product. And I'm going to go ahead and circle that product, because if I ask you to show me the major organic product of this reaction, what you would need to provide is just the structure that I've shown here. On the other hand, if I ask you for the major organic product and the mechanism, you would need to show me these electron pushing arrows, formal charges, lone pairs, all that good stuff, and the final product of the reaction. Jumping into another example, we're asked to predict the major organic product and the mechanism of the reaction. We have our metal alkoxide here listed on the right, and our alkyl halide listed on the left, keeping in mind that it's a primary carbon directly bonded to the bromine leaving group, so we can expect this will proceed by our SN2 mechanism to give a Williamson ether synthesis. So in this reaction, we will take, writing out the mechanism for this, the structure of our metal alkoxide, and specifically focusing on the alkoxide anion. We take that negatively charged oxygen, and we bring that oxygen in using its lone pair of electrons as a nucleophile to attack the electrophilic carbon here that's bonded to our bromine leaving group. The bromine leaving group breaks away, and the product of that is going to be a bromide anion, as well as our organic product. And thinking about our organic product, we've ramped things up a little bit here because we do have a chiral center in our starting structure. And looking at our chiral center, our starting structure, which I'm circling with my laser pointer there in the middle of the screen, there's nothing happening specifically at that chiral carbon. So there's no way for this stereochemistry of that chiral carbon to invert from R to S or S to R. So we need to just make sure that we draw the absolute configuration the same here in the starting material at that position as we do in the product. The easiest way to do that is just to replicate that. And so that's what I have done here, is I've taken my alkyl group and I've drawn it exactly the same with my oxygen up here. And now I'm going to link that via the new covalent bond that we formed with our red electron pushing arrow. I'll show that in red here to color code it, to the chain of 2 carbon atoms, 1, 2, that is directly bonded to our 3-membered ring, like so. So therefore, the final full structure of our major organic product of this is what I'm circling here in blue. This is our ether product. As one final example, a type of problem you may also come across is you may be asked to propose a way to synthesize the following ether using Williamson ether synthesis. In such a type of problem, you would need to design what you would use as the metal alkoxide structure and what you would use as the alkyl halide, keeping in mind that the alkyl halide absolutely has to be a primary carbon directly bonded to the leaving group as your main restriction in designing this. So let's go ahead and try to synthesize the following target. So we're going to try to synthesize this particular ether molecule. And in synthesizing this ether molecule, we have to think backwards about how we would go about doing that. And we looked earlier at the general generic template for Williamson ether synthesis that said ROM, where the oxygen anion there would attack the carbon that's directly bonded to the leaving group of our R prime to give an SN2 reaction, forming a new bond between the oxygen and the R prime. This was our general paradigm, and we want to fill this in specifically, keeping in mind that we want our exact RO R prime structure to be this ether product that we show up here. So what can we make our starting structures out of here? Keeping in mind that the CX has to be a primary carbon. So in order to do that, in order for Williamson ether synthesis to work, period, what absolutely needs to be the case is that one of the 2 carbons, or both of the 2 carbons that are directly bonded to the oxygen of the product, need to be a primary carbon. So here, that's definitely not a primary carbon. It's a tert butyl group. So that's not going to work Over here, on the other hand, though, we have a primary carbon. If neither of the two carbons highlighted in blue are primary carbons, meaning they have just one other carbon atom bonded to them, the Williamson ether synthesis will not work. Instead of giving an ether product, it will give an elimination reaction to give an alkene product. So, keeping this in mind, this right hemisphere of the molecule is what we need to derive from our alkyl halide in our template. And so filling that in, our R prime group in our template that's bonded to the leaving group of that R prime template is what's replaced with the oxygen in the product. So following that template, that means that we can use as our halogen atom here, a chlorine or bromine or whatever halogen we like, plug in the appropriate length chain. So it's a 4-carbon chain, 1, 2, 3, 4, 1, 2, 3, 4. And so that's our 4-carbon alkyl halide. Then the other reactant here would be our tert-butyl group directly bonded to that oxygen nucleophile. So that structure that we've drawn follows exactly with what we see in our product here versus here is what our reactant's looking like, and have that bonded to our favorite +1 metal, such as sodium. And so to verify that this would work, you could sketch out the mechanism if you like, imagining that the oxygen's lone pair electrons come in, form a covalent bond to the carbon here as the leaving group leaves, and indeed that would give you the indicated final major organic product. So what you would need to put down is that you'd have this metal alkoxide reacting with our 4-carbon alkyl halide. And again, just as a closing reminder for this, the key trick is that the carbon that's bonded to the leaving group has to be a primary carbon. So we couldn't have put the tert-butyl group over here and used the propyl group on this side of the reactants. Instead, it has to be the case that the primary carbon is what's bonded to the leaving group. Otherwise, the reaction will give elimination instead of this SN2 substitution.